Hello everyone, this is another IB Physics past paper review. This is May 2018, paper 1, standard level, and this is page 9. Here we have question 16. A system that is subject to a restoring force is oscillating about an equilibrium position. So I've gone ahead and drawn a little diagram that you should be familiar with. This is just our mass, which is this red box, suspended between two springs that are attached to a wall. So we can obviously think about this box as having, or this mass as having an equilibrium position in the middle. So this would be at rest. And then if we moved it, if we stretched it to the left a certain distance and let go, it's obviously going to bounce back. And if this was a perfect ideal system with no friction, this would just keep going forever. So we have a couple of things to think about. We have some forces to think about, and we have some energy to think about. So just to laser us in on the part of our data sheet that's relevant, here it is. So we can see that we've got our potential energy of a string formula here. Sorry, potential energy of a spring, which is half kx squared, k being a constant value, x being the displacement. We'll also consider I'll just move this over there. There we go. We'll also consider the restoring force as we think about this system to try and answer this question. So what is the question? Well, it's saying that for a motion to be simple harmonic, in other words, an ideal system with no friction, the restoring force must be proportional to, well, this is where we need to think about what's happening in the system. So let's go ahead and imagine that we do stretch this red mass to a point over here. Okay, as it's stretched all the way, if we were to take this red mass and bring it all the way over here, there will be a restoring force. Okay, so I'm going to put there's a restoring force, and it's going to be at its maximum, the maximum force at this point, and this force is going to be pushing it to the left. Sorry, to the right. We can also say the same thing if we did exactly the same thing over here, or even if we released the red mass from this point. If there was no friction in the system, we would expect it to go all the way to an equal distance or an equal displacement on the other side, at which point it will have a force max, except this time it's going to be going in the opposite direction. It's going to be restoring it back to the middle. In the equilibrium position, the force is going to be 0. So there's no force in the middle. Okay, so it goes back and forth between the maximum force, 0 force, maximum force, 0 force, maximum force, 0 force, and back and forth. Of course, we also have some energies to think about, because in our question, we have to think about the amount of the oscillation, or the height of the oscillation, the amplitude of the oscillation, the displacement, the energy, and the period. So let's think about energy. If this is moving back and forth, okay, we can represent this. We've probably seen this represented as a sine wave. Let's go ahead and do that. So if we were representing it as a simple harmonic motion, we would expect to see a sine wave like this, and we could represent that as the displacement over time. We would talk about this here being one period to do a full oscillation, etc. If we think about the energies, well, as it's moving back and forth, we have a transfer of energy. We're going to have some potential spring energy, and as it's moving towards the equilibrium position, there's going to be no spring energy, but there will be all kinetic energy, and then that's going to be converted back into potential energy. So we can represent this as saying in the middle we have EK, and at the edges we're going to have a 0 velocity, which means there's no EK, but all spring energy. Okay, so let's do that. Spring energy here. And in between the maximum displacement and the equilibrium, somewhere in here, there's going to be a combination of spring potential energy and kinetic energy. What's Important though is our equation. Our equation is saying that the potential spring energy is proportional to the displacement squared. So it's not going to be evenly distributed. In other words, half of the displacement. So let's go ahead and put this in as a red dotted line here. This bit here would represent half the displacement. So the question is, at this point here, in other words, half the displacement, so from going from zero displacement, maximum displacement, half the displacement, is it going to be half the energy? And hopefully you can see from the formula here, this guy here, that the energy, the potential energy from the spring is proportional to the displacement squared. So in other words, at this point here, this is half the displacement. It is not equal to half the energy. Whereas, hopefully you can recall, if we're just talking about the force, okay, the force is going to be equal to kx. In other words, the force is proportional to just the displacement. So at this point, let's do another arrow in here. At this point here, the half displacement point, so let's go half the displacement is equal to half the force. Okay, so hopefully that's clear. So let's look at our options. Option A is the amplitude of the oscillation. So once it's in simple harmonic motion, it's saying the restoring force must be proportional to the amplitude. Well, the amplitude of the oscillation is just how much this is going up and down, which is going to be the amount of displacement. Now, if it's in simple harmonic motion, then we're assuming no friction, so this is going to keep going up to the same height all the way along. In other words, if we were to look at our sine graph, I could do a horizontal dotted line representing the peaks, and it should be exactly the same peak all the way along forever. My drawing isn't very good, but this should match. So the peak of the graph is going to be the same all the way along. So it can't be this. That's not going to change. It's got nothing to do with the restoring force. It's just how far it's gone up and down in the sine wave. The displacement from the equilibrium position, well, that's to do with this little statement that we just made here. And we just said that the displacement at half, it would be equal to half the force. And at displacement 0, it would be equal to 0 force. And at displacement max, it would be equal to the force max. So it's looking a lot like this is our answer, but let's keep eliminating them just to make sure. C is the potential energy of the system. Well, that's to do with the statement that we made down here, which we because of this square function, we're saying that is not proportional. So it's not this one. And the period of the oscillation, well, that's not going to change either. And it's just going to go back and forth. The time with which it takes to go back and forth, in other words, the time between complete wavelengths on the sine wave is not going to change. And it's not got anything to do with the restoring force. It would be to do with some other factors, probably to do with this K value here, how much, what the constant would be in this statement. So it's not going to be this either. So we're pretty confident now, based on this statement here, that the answer should be B. All right, so for question 17, here we have a particle being displaced from rest and released at a time t0, performs simple harmonic motion. So it says it's a particle, but really it doesn't matter what it is. It's an object being released and performing simple harmonic motion. Which graph shows that variation with time of the kinetic energy of the particle? So the fact that it's released from rest is crucial, so I'm going to highlight that. It's released from rest, which means the velocity, initial velocity is going to be 0, which means the kinetic energy initial is going to be 0. So at time, this means, so therefore, at time 0, the kinetic energy should be 0. So we can look for that on the graph. So let's have a little look. Graph A at time 0 does not have kinetic energy of 0. So I can say that it's not going to be A. At time 0, yes, B does have the option, so it could be B. But then if you go to C, C at time 0 does not have kinetic energy of 0, so it cannot be this one. And then again, D does have this kinetic energy at 0 at the 0 time point. So it's either B or D. And as far as we can tell, the amplitudes of the graph look very similar. They both start from 0. So what else do we know about kinetic energy? Well, can kinetic energy be a negative? Because that's really the only difference between these two graphs. The only difference is the positioning of this 0x axis. And so in graph B, at this point on the graph, this all represents a negative energy. So at this point, we would have a negative EK. And in Newtonian mechanics, this is not possible. Energy is a scalar value. It cannot be a negative, which brings us to D, and hopefully you can see D is the correct answer.